Hello, everyone. Welcome to the Mindscape Podcast. I'm your host, Sean Carroll. You may have heard there is a crisis in physics. No, there's not. I mean, there's little tiny crises, but that's the very standard procedure if you're doing science at the cutting edge. There's all sorts of puzzles that we don't know the answer to. I did a long solo podcast about it last year. Don't worry about it. You can check everything out there. But look, you have to be honest, there is something weird about the present state of particle physics, of fundamental physics, as we talk about it. The crisis in physics talk is not at all about, astrophysics or condensed matter physics or atomic physics. It's really about the standard model of particle physics, our best current theory of the fundamental laws of nature and the elementary interactions between fields and particles. And that's because the standard model has this strange status as a theory that fits all the data. As far as we know, there's, again, little anomalies here and there that we could talk about, but for the most part, for decades now, the standard model has just fit all the data. But it's certainly not the final answer. It's definitely not the final theory of everything, for obvious reasons as well as for subtle reasons. The obvious reasons include that it doesn't include gravity, it doesn't include dark matter, it doesn't explain the Big Bang, the difference between matter and antimatter in the universe, and so on. But also the more subtle reasons are things like it looks ugly. It's both ugly and beautiful. You really have to dig into the standard model to appreciate what's going on. It's ungainly, let's put it that way. There's a lot of moving parts. The weak interactions treat left-handed particles and right-handed particles differently. The strong interactions don't. There's different generations that seem just like copies of each other, but they're a little bit different. The different particles have different masses, which basically seem pull out of a hat. We don't know why all these masses are what they are, and so on and so on. It does not look like the level of austere compellingness that you would expect a final theory to have. And that feature of the standard model, the fact that it is kind of bizarre, kind of weird, kind of ungainly, is reflected in how it came to be. That's what we're talking about today. We have Chris Quigg, who is a particle physicist, theorist at Fermilab, and who has written a book with Robert Kahn as his co-author called Grace in All Simplicity, Beauty, Truth, and Wonders on the Path to the Higgs Boson and New Laws of Nature. So basically the idea is that Chris Quigg and Bob Kahn, who are both very good writers and who lived through much of this history, have written a book that tells the history of how modern particle physics developed, the standard model in particular, up to the Higgs boson, like the subtitle says, with an emphasis on all of the twists and turns along the way and the human beings who made it happen. So it's not like the book that I'm just trying to finish right now, a bunch of equations about gauge theory and symmetry breaking and things like that. It's a bunch of stories about people and how they lived and the decisions that they were making. Because while you're doing science, while you're in the middle of it, you don't know whether a certain approach is going to work or not work, etc. Sometimes, as Chris will say in the podcast, you get the right answer and you don't even know it yourself. You don't even trust your own equations. Going back to Paul Dirac not quite trusting the prediction he made for antimatter in the Dirac equation. So I think that this discussion that we're going to have here illuminates a lot of how the standard model came to be, which is just a giant, bizarre Byzantine story. You can tell the story of the origin of general relativity, and it's mostly Albert Einstein. He had help. He was talking to people, but it's mostly that one guy. Even the origin of quantum mechanics, it becomes pretty clear there were a couple of different strands, that led to Heisenberg and Schrödinger, and then Bohr and Einstein and their friends had to duke out how to interpret it all. But it does, fit into a relatively compact container, whereas the standard model is just so many names, so many particles, so many ideas and concepts that had to be invented. Despite the fact that we get into the weeds a little bit in what some of those concepts are, we don't get nearly as into the weeds as we could have. Let's put it that way. But I hope that not only will this conversation convey some of the interest and excitement of the standard model, but also help people understand the mindset of physicists as these things are going on. You have some new experimental discovery, it doesn't fit in, or you have some new theoretical idea, it looks too good to be true, how can you apply it, right? You're going to guess right sometimes, you're going to guess wrong sometimes. That's the story of our lives, and it's led us to a pretty good place in modern fundamental physics. So let's go.
Thank you, Sean. It's a pleasure to be with you.
So you've written this wonderful book. Now, it's about particle physics, modern physics, etc., and that's what you do for a living. But it's a different kind of book than I'm used to reading about that subject matter. You know, we both come across many such books, but you've taken two things. Number one, a kind of historical angle. You go into much more detail than average about the personalities, the events that happened. But despite the fact, number two, that you have a historical angle, it's not in chronological order. You hop back and forth a lot, which maybe is more like how real physicists think about their background and their history. But before we get into the physics, tell me a little bit about the book. Like, what made you write it this way with your collaborator, Robert Kahn?
Yes, so you've hit an important point for us, and that is that the way science progresses, the way we physicists think, is hopping around here and there. There are many things that we hear for the first time and that don't make an impression on us the way they should have. And there are also many experimental technological innovations as well as theoretical ideas that, when first proposed, are applied to what turns out to be the wrong problem.
Mm-hmm. We'll see that coming up.
Luckily, we have memories, at least some of us in our community. We have libraries. And so these ideas or techniques can later find good application. So that was part of it, that we wanted to get away from the strict logical progression.
Yeah.
Because even in our own work, we haven't known things to go that way. And certainly in the grand sweep of science, that's not the way it goes. We wanted to pay attention to and show our respect for the people who do science now and in the past, not just the ones who have the fancy ideas or are lucky enough to make the great experimental or observational breakthroughs, but people who contribute to the technology and to the techniques that allow us to push forward. So that was the idea. It's a love letter in a way to many of those people. And our other guiding principle was that we were writing for people we would like to have a conversation with. Now, as you know, in your podcast, in a book, conversation seems kind of one-sided because only one person is emitting at a time. Nevertheless, the way we think about it, I'm sure this is true for you in your classes even, is that you imagine people should be talking back to you, altering their opinions, maybe objecting to what you say, and so on. And so that's what we set out to do.
It's wonderful, yeah. And so I'm going to disappoint you right from the start because your book is too long for us to cover everything interesting in the scope of this podcast. So I was thinking really hard about where to start, and I think that maybe Emmy Noether is a good place to start because symmetry plays such an important role in your book, and you have some great stories, or at least some great color about her life that I wasn't aware of. So talk a little about Emmy Noether and what is the role that she plays to the modern physicist.
Very good. Let me start with the way we introduce that chapter, which also represents one of the ideas that we had in writing the book. Not to give physics lectures, not to have an examination at the end of every chapter, of course, but to engage people in topics that they've already perhaps heard about or thought about, and then use those as ways of getting into the physics or mathematical content that we want to talk about. So we actually begin that chapter that introduces Emmy with a little discursion on Louis Sullivan, the famous Chicago architect, that you will remember from your time here, who enunciated the principle that form follows function. He was rebelling against the neoclassical tradition in which every building had to look like a Roman temple, and argued, chiefly in the context of department stores and warehouses and things like that, that the building should actually look like what it does, and you should be able to tell what it's going to do. So he had a slogan, which is summarized in architectural school, design school, and such. Form follows function. And you will know, and our readers will now know, that we physicists have, for about the past 50 years, understood that it's a good idea to turn that slogan on its head and to say the function follows form, which is a sort of pithy way of saying that the fundamental interactions of nature, the forces that we talk about, follow from symmetries, from the form of things.
Mm.
So that idea originated in its general form in work that a German physicist, German mathematician named Emmy Noether did in 1918. She's a very interesting character. She was the child of a mathematician. Her brothers were mathematicians, but she was a girl, which meant that there were certain obstacles to her pursuing education and a career. Her original studies were in a fancy school in Erlangen, where she grew up in Germany, for promising young women of an aspirational group. And she was certified to teach foreign languages, namely English and French. However, because of her background and her native ability, she was taking instruction on the side in mathematics. She applied to the university in Erlangen, where her father was a member of the math department, and it was not possible for a young woman. That would be too disturbing for a young woman to enter the university, so she couldn't do that. She applied for permission to audit courses, and that was given on the basis of this private tuition that she'd taken from mathematicians. And so she was able to listen in. 1 year later, after her failed entry into Erlangen, she was admitted to the great university of Göttingen, where every great German mathematician that we've ever heard of either passed through or was in residence. And I think her first semester there, she heard, I guess Gauss was dead, but she heard lectures from Courant and Hilbert and Klein and Schwarzschild, people like this. So I've said to my students when recounting this to them that if that's your first semester, either you're history or you're hooked. So luckily for us, Emmy Noether was hooked. The authorities relented a little bit. She was able to enter Erlangen as a graduate student and took her PhD there from an interesting man named Paul Gordon. Physicists know this person from his work with another man named Alfred Klepsch.
Oh, no, I hate these people.
I mean, there actually were people who gave us these famous coefficients that we worked on. And she wrote a thesis for him that was heavy on computation, and which she described after the fact by the colorful German word Mist, M-I-S-T, which means, in a polite translation, dung. And which I first encountered in high school when I was reading Faust, because one of Faust's misadventures is to end up with his head stuck in a pile of dung.
Yeah, okay, good.
And so that resonated with me. Anyway, so in 1918, she wrote this wonderful paper. She had been engaged by Klein and Hilbert to help them out. They were puzzled about some aspects of the general theory of relativity, which was new at that time. And in particular, you, having written a textbook on the subject, will know very well that energy conservation, this fundamental law that we use everywhere, doesn't look the same in general relativity as it does in the rest of physics. It looks sort of like an identity or something rather than a constraint. And Klein and Hilbert were puzzled about this, so they brought her back to Göttingen. And she chatted with them and did things. On the side, then she wrote this famous paper in which there are two theorems. And the theorems have to do with the connection between symmetries, a sameness before and after you make some operation. You know, think of a drop of water in the absence of gravity. It's perfectly spherical. You can look at it from any direction. It's the same. And what she found in the first theorem is that every such symmetry is related to a conservation law. So turning things around is related to the conservation of angular momentum, the famous thing given by the ice skater analogy. Independence of time is related to the conservation of energy, and independence of place, the conservation of momentum. This is a fantastic breakthrough in a sense, because until this time, people were still fooling around trying to understand what were the quantities that were useful to talk about as conserved. And the conservation laws were empirical regularities.
Exactly, yeah.
Now you know that they come from somewhere. And so if you give up energy conservation, it must mean that the laws of nature are changing in time in a predictable or unpredictable way, and so on. So that by itself is a great insight. Now, pieces of this were known before, so I think it didn't make too much of a splash, because physicists said, oh, yeah, I could have worked out that particular example. I should have known this, and so on. So it didn't get people jumping up and down. The second theorem is even more powerful, and it is the basis of the way we think about the fundamental interactions today. And that is that if you allow these symmetry operations, these changes, to depend on the time or the location at which they're done, you can also make theories of that kind. But in order for that to work, there has to be some communication of what's happened, what you've done at one place to another place, so it knows how to catch up and do things. And that, it turns out, when properly understood, is the basis for the fundamental interactions, because you need a messenger to go from here to there. At about the same time, Hermann Weyl, a famous mathematical physicist, and one of the people most responsible long before we were born for introducing symmetry concepts into fundamental physics, had his own idea that he could make a unified theory of all the fundamental interactions.
Some things never change.
There were two fundamental interactions at the time, gravitation and electromagnetism. And he had this scheme that we now think of as cockamamie, in which the size of a measuring rule would change, the intervals would change from position to position, and that would give you electromagnetism and gravity. It doesn't. Poor Hermann was trying to do this before quantum mechanics had been invented, so he was working at a certain disadvantage. There's a lot of back and forth. Einstein himself pointed out to Weyl that if that were the case, then the outcome would be dependent on the path you took to go from here to there, and that sounds like a no-no. Then quantum mechanics came, and other people helped him out, and by the end of the 20s, he understood that you could do an Emmy-Noether-like transformation, but of a very weird kind, in which the thing that you're changing is not the measuring stick or the direction, but the quantum mechanical phase, the phase of the quantum mechanical wave function. And that leads you to electromagnetism. It makes it obligatory to have a photon, a carrier of electromagnetism, and so on. Okay, so that was great progress.
I'll just interrupt just for a second to say it's all, you're kind of breaking my heart here, because I just finished copy editing my next book, which is called Quanta and Fields. It's a popular level book about quantum mechanics and field theory, but it shows people all the equations. So I talk about what a connection is, what gauge transformations are, but it's very short. I'm not allowed to ramble on for too long. And so like this historical background of Weyl and Noether, and I wasn't able to talk about any of that stuff, but it is fascinating.
Yeah, I want to say that I'm looking forward to that book, because back in my days as a professor, I was given the gift of teaching graduate quantum mechanics, which you will know is a fantastic course. And it opens the world to your students. Back in those days, it was before quantum information was a topic in such courses. So I'm looking forward to learning what I didn't teach in those days.
I will let you know, Chris, that my graduate quantum class was not a wonderful experience, actually. That's not uniform. That's not a symmetry.
Well, I didn't say that mine was for my students, but it was really great for me.
Anyway.
Okay, so here's what we now recognize as a fantastic tool. Nobody jumped up and down about it. Nobody applied it in different ways. And I think there are two reasons from that. Professional historians perhaps have gone into this, or if they haven't, they should. Here's Göttingen. Göttingen is one of the places quantum mechanics is being invented.
Yeah.
And it is this temple of mathematics. Anybody who ever was anyone after Plato or somebody, Archimedes, was in Göttingen at a time, going back to Gauss, who is if you look at our scientific heritage, all of us are descended from Gauss because he was the only one at the time. So they didn't do anything with it. Now, why could that be? I think there was a lot of interplay between the physicists and the mathematicians. Courant and Hilbert wrote their famous book on methods of mathematical physics, which is one of the few places where you actually find a mention of Noether's theorem. It's about 2 paragraphs. And I think the reason for this, other than there was stuff to do, was that there was no other symmetry to apply it to.
Right.
It was another decade before isospin, the similarity between protons and neutrons, was recognized, because after all, you needed a neutron to be discovered before you could posit a symmetry. There's a wonderful report from Werner Heisenberg, who was one of the inventors of isospin, conceived the notion. And he confesses that he never read Noether's paper.
Yeah.
And I think, again, it goes back to when you hear the first applications of it, you nod your head and say, oh, yeah. And so, no. And I have to say, a couple of the gods of the generation just above ours have told me they never read the paper either. It was part of the air, but it was part of the air in a rather distilled form. So the application of this in a way that we think of as modern came in the 1950s, when C.N. Yang and Bob Mills had the idea that instead of just using isospin symmetry, this similarity or sameness between protons and neutrons, if you ignore electric charge, as a way of doing classifications of nuclear levels and stuff, to say that could be a position-dependent symmetry that you impose. And the way Yang put it, I had the good fortune to learn it from his lips, was almost a statement of democracy, that if I get to choose the convention for what's a proton and neutron, shouldn't you get to choose your own? Shouldn't everybody in every seat in the auditorium get to choose? So they worked that out, and they found, following Noether's second theorem, that it gives rise to a theory of interactions among protons and neutrons. So people were looking for that, a theory of nuclear forces. It had the little shortcoming that it didn't have any pions in it, which we now know are the dominant force, the dominant source of the nuclear force. And the force it did have was photon-like, so zero mass for the force carriers, infinite range, which wouldn't explain the fact that the nuclei are all teeny tiny,
right,
or at least tiny.
Short range forces, yeah.
So it's one of these examples that we encounter frequently of a brilliant penetrating insight applied to the wrong problem.
I want to dig, of course, much more into that, but I just want to take advantage of having you here, having just written this book, to fill in a couple of the personal details with Noether, because number one, I get this weird impression that obviously there's a lot of discrimination against women at the time, but the very top people, your David Hilberts and your Albert Einsteins, absolutely appreciated her. It was sort of the background bureaucracy that made her life very hard.
Yes, so she had 3 strikes against her. She was a woman, she was a Jew from a Jewish family, and she was a pacifist. Not only a pacifist, but one whose best friends, other than the ones in Göttingen, were in Russia. And this made her an object of deep suspicion for the Nazi characters. Even before that, she was a subject of discrimination for all of those things. She had a brief flowering of her career in Göttingen when, after the First World War, the Weimar Republic came in and had lots of reforms, wokeness, people would call it today, and removed many of the barriers. So she began to have a more regular career. Hilbert and Klein had before that announced courses that they would give, assisted by Fräulein Noether. The principal would show up for the first class. This may be a tradition in some universities, and say, "Hello, students. Here I am, the great man. Tomorrow you'll hear from Fräulein Noether," and she would give these courses. So she was probably paid under the table or something from that. After the reform, she became a Privatdozent and could be paid directly by students. And in Göttingen, with all these gods around, she, of course, was younger than many of the gods and probably a little friskier. She attracted a coterie of really devoted students, many of whom wrote textbooks that at least I read in my youth, and maybe you did too. And there are great stories of them following her. She loved to walk and talk at the same time. And there are great stories of Emmy leading her Noether boys around Erlangen in a rowdy bunch, according to the locals. And they'd go around and around, and she's always talking about mathematics. She gave a lot of lectures. One of her peers was a man named Émile Artin, who also was a famous lecturer. I think he ended up at Notre Dame later on. And I read one of his distillations of their work. The two of them were inventing modern algebra together with their students and others. And the transcription and translation of the lectures so that ordinary mathematicians, if not ordinary people, could understand them, was done by some of these followers.
I really liked that anecdote in your book because it fills in some of what it must have been like, because you hear about Noether, obviously great mathematician, made amazing contributions and suffered discrimination, etc. But there was joy there too, right? It wasn't all like discrimination and annoyance. Like there was, like you said, friskiness and rambunctiousness, which is great.
Yeah. There are other stories of people enduring a long seminar, walking home through the rain, and Emmy just wants to stop on every street corner and talk about the lecture, and they just want to get in out of the rain. So if we could only all have exactly that much enthusiasm, what could we do?
Okay, so we just have to pass over lots of good things because there's too much history here. But let's skip to the 1950s, where you've already sort of led us to with Yang and Mills. So Noether and Weil have this idea that symmetry somehow really important, right? Not just leading to conserved quantities, but even maybe leading to forces of nature. What was in the 50s? Like, what would people have said, professional physicists, if you said, what are the forces of nature? Like, quantum field theory had been more or less established then, right?
Yes. So quantum electrodynamics had been invented and perfected to the taste of almost everyone except Dirac, who objected to the way we make calculations and felt that there must be a better way, which all of us would not object to if we could only find it. So that by that time, the nuclear force binding protons and neutrons together into nuclei had been established. And the weak interaction was identified. This is the one first responsible for radioactive beta decay, so the emission of an electron by a radioactive substance. For a brief moment, it was imagined that those two were the same, but they're not, as experiments showed. And the theory of the weak interaction, beta decay interaction, was invented in the 1930s by Enrico Fermi, cloning and generalizing what Paul Dirac had done for quantum electrodynamics. And it had a very important idea in it. And that is that the electron that's emitted by a radioactive nucleus wasn't there to begin with. So it wasn't living inside the nucleus, but that it was created at the instant of decay. So kind of spooky, but not as spooky as what you'd have to say if it were living inside all the time. As became clear when the first positron decays, anti-electron decays were seen, because that would be really weird for antimatter to be living inside the nucleus. Fermi invented this, as I say, Fermi had written a scan on Dirac's theory of quantum electrodynamics, which even in my days in graduate school, we were advised to read, a famous paper in Reviews of Modern Physics. So it's before Richard Feynman and others, but quite brilliant in its conceptualization of things. So he generalized that for the weak interactions. And to a large extent, at least until the time I was born, that was the theory of the weak interactions.
Can I ask
please.
a slightly technical question? But these days we do, and we will in the rest of this podcast, talk about quantum field theory, right? Mm-hmm. Electrons and neutrinos and positrons are all vibrations in quantum fields. My impression is that wasn't the way you would have talked in the 1920s, like that electrons were particles, the electromagnetic field was a field. And I tend to give Fermi a little bit of credit for starting to think of the matter particles as fields and really doing field theory. Is that right, or am I just projecting?
Well, he was a heck of a guy, so I'd give him credit for lots of things. I think that actually began with Dirac.
Yeah. Okay.
1928 to 1932, and we tell stories about Dirac in the book. I had the opportunity to meet Dirac a couple of times, and one of the stories we tell is there was a time I thought he was quite ancient. In fact, I thought he was so ancient that he must have been reconstituted for the event. And I think he was younger than I am now. So, it was the third or fourth time I had met him. I gave a colloquium on quantum mechanics, and the great man was sitting in the front row, smiling cryptically from time to time. So I took that as a good sign,
Tough
whether
crowd,
it was meant as a good sign or not. And there's a cocktail party afterwards, at which I finally got up my courage and said, Professor Dirac, I've been wondering about this thing that puzzles me. When he made his theory, and there had to be a counterpart to the electron that had positive charge, he tried to interpret that as the proton, which, if you trust his equations, was nuts, as I think he knew. And it turns out to be the anti-electron, the positron. Yeah. And so it's very mysterious why this man who trusted beauty and mathematics and rigor so much. And he was a marvelous character. So he always would have a pregnant pause before he answered. And in this case, he took longer than usual. And I could see his eyebrows wrinkling in an interesting way. He put his chin down on his chest the way he usually did, but he kept it there for a long time. And during that time, he allowed me to estimate just how long a line of young fools I had just joined by asking this question. And then he said, he actually confessed, sort of. He said at that time, it just wasn't respectable to propose new particles. Now, he was partly criticizing people who were of my generation who were introducing new particles every day. But it was, and then he elaborated a little bit. I think he looked back on it as a slight failure of nerve, which we from the outside might have guessed, except that he was a really clever guy, so we expect him to be immune to such things. Anyway, so that was an opportunity to hear at least some version of the story from one of the creators.
Well, I think that this next place we go with Yang and Mills and gauge theories is it a wonderful example of nerve, or trying to say, well, okay, this isn't working, but we're going to do it anyway because maybe someday it will work. So Yang and Mills knew about symmetries. Presumably, they knew about Noether's theorem.
So
did they?
That is a wonderful question. Yeah. Whether they knew about it at the time. Later in life, when I heard these stories from Yang, later in his life, it was clear that he had deep respect not only for symmetry, but for Noether's accomplishments. With the degree to which that was in his head in 1954, unclear. I don't have an authoritative source.
Okay. But what's amazing from our current perspective is the symmetry that they looked for or tried to take advantage of was treating the neutron and the proton as two different identical things. And it's true that for some purposes you can do that, but they're clearly not. I mean, maybe you as a working physicist can explain to our audience of non-working physicists, why would you ever treat the neutron and the proton as more or less the same thing, and how did it not work?
Well, you would treat them as the same thing for the same reason that when you're studying classical mechanics, Newtonian mechanics, and you think about throwing a ball through the air, you neglect air resistance. That the first idea that you can get of how things are going to go is just say, there's no atmosphere.
Yeah.
I'm just going to worry about gravity, no spin on the baseball seams and things like that. So it's an approximation. They are two particles that have, in fact, the same strong interactions we've learned through experiments. They have very nearly the same mass. You can sort of say that what's the difference between the two? Well, the difference between the two is that the proton has a charge and the neutron doesn't.
Yeah.
Now, so the first thing you'd say is, well, proton has a charge, the neutron doesn't, so the proton should have a little electromagnetic energy and weigh more than the neutron, except that it doesn't. It's the other way around for reasons that have to do with details and that we all know about now, but you wouldn't have. If we were making the world, we probably wouldn't have made it that way.
Right.
Although it's good for us that we have, because it makes the proton stable. So what's interesting about the Yang-Mills theory is that although everybody said it's not the theory of the nuclear forces, physicists, especially those practicing field theory in my childhood, were fascinated by it. And there were many people who tried to do something to the theory that would make the force particles massive so that the nuclei could be in finite size rather than as big as they wanted to be. Lots of good work was done there. Most people didn't get the right answer. The right answer turned out didn't have to do with nuclear forces at all, because without fooling around in that way, if you apply this strategy, not to isospin, but to the color symmetry that we attribute to quarks, the more fundamental constituents, you get the theory of quantum chromodynamics, which, as we call it, is a new law of nature.
Yeah.
That tells us how protons come to be and neutrons come to be and so on. So the way this was applied successfully a little before quantum chromodynamics was with the insight that this could form the basis of a theory of the weak interactions. Many steps along the way. The weak interactions was learned in 1957 by a couple of brilliant experiments that we talk about, distinguishes left-handed and right-handed interactions. The particles concerned, like the electron and the neutrino, have left-handed pieces and right-handed pieces, just like we do. And they're similar but not the same. And whereas in electromagnetism, the left-handed electron and the right-handed electron have the same charge, so they behave the same way in reality and under symmetries, the left-handed and right-handed electrons don't. And so the symmetry that you'd like to make has to be hidden, as we say. And the right analogy from that came from the phenomenon of superconductivity. Superconductivity, everyone knows, has a great miraculous property, that there are these substances that, when cooled to very low temperatures, conduct electricity without any resistance. They don't heat up, they don't glow and anything. You start a current, it'll go forever. A vast technological importance, even for the magnets that we use to build our accelerators today. But superconductivity has a second magical property, which is that magnetic field can't penetrate very far into a superconductor, which means, in the funny way that physicists think, that inside the superconducting medium, the normally massless photon acquires a mass. Well, the photon is still coming from a symmetry principle, but in this special substance, the special surroundings, it becomes massive. And that is a model for how the force carriers of the weak interaction could acquire a mass. That, in some, some weird way, we're all living inside a metaphorical
Yeah,
superconductor,
exactly. I mean,
and all the better for it.
I do want to dwell on this because I think it's an interesting insight for that's hard to convey to people who don't do science for a living. Yang and Mills and their friends, so they knew they were in the atmosphere, whether they had literally read the paper or not. There was this idea that symmetries could lead to forces, and they were just trying to implement this. And there's an obvious problem. The neutron and proton didn't look very symmetric. One had a charge, the other one had a different mass, etc. But they bulldozed forward anyway, and they found more problems. Like, oh, there's supposed to be massless particles. We don't see them either. And yet, like you just said, it was so beautiful that people said, well, we're going to keep trying. We're going to keep banging our head at it and trying to make it work. I don't think I want to hear your viewpoint on this, but one could make the same or one could argue that's analogous to what string theorists are doing right now, right? You have a beautiful structure. It looks very different than the real world. It's in 10-dimensional space-time, and there's 10 to the 500 different vacuum states. But the people who are in favor of this theory say, it's just something like this has got to be right. Let us keep working on it, and we'll find it eventually.
So I think there is an analogy, and it's one that I don't know enough to describe very well, but I'll tell you a little bit more about the Yang-Mills theory. When I was at Stony Brook, Jim Simons, famous quant and mathematician, was in the department. We were all in the same building, on the same floor. And he and Yang decided that we should get the mathematicians and the theoretical physicists together. Great idea. And the first topic was going to be Yang-Mills theories. So there was an evening, there might even have been wine, I don't remember. And Yang explained his very physical democratic motivation for stumbling on Yang-Mills theories. This was stunning to Jim Simons, who had invented the same mathematical structures called fiber bundles by pure reason, without, saying, it should be my choice and your choice and protons and neutrons and all that. And the next week, Jim Simons gave his discovery path, pretty unintelligible to me, I have to say, in which Yang was stunned by the notion that without reference to physical reality, you could come up with the same concept. I suspect a lot of what's going on in string theory and the attempts to relate it either to problems in particle physics or information, when understood, we may find that there's a similar duality, and that various smart people who are coming from one direction or the other may in fact meet someday. And that would be fun to see.
Right. And the most fun is the fact that it's also possible that it's all just wrong, right? Like Yang and Mills could have been wrong. You don't know ahead of time.
Exactly right.
You have to do the work.
This is one of the seductive aspects of the Nutter strategy. You can apply it to any old symmetry that you think you see in the universe. And for most of those, it does not lead to a viable theory. Well, it leads to a mathematically viable theory, but it doesn't lead to a theory of this world.
Right.
So you can still apply it in the wrong way.
Well, and I think that we need to give some explication to symmetry breaking, because basically, to give away the game, because we both talked about this in different formats, and I'm sure the audience has heard about it. There's two really interesting ways in which the Yang-Mills strategy is implemented in the real world, but both are extremely subtle and unintuitive. One in the weak interactions, one in the strong interactions. And so for the weak interactions, all the complaints we've been making about Yang and Mills are basically right. The two identical particles are the electron and the neutrino. They look very different, but the symmetry is broken, and that makes it all work.
It's true. What would you like me to say?
Well, I guess the journey to get there, because my impression is that when Brow and Unglair and Higgs and everyone was thinking about breaking symmetry, or even, I guess, when Nambu and Goldstone were thinking about spontaneous symmetry breaking at the very beginning, they were mostly thinking about the strong interactions, not the weak interactions.
Yes, so there are six people who basically had the insight of how you could hide a symmetry in a gauge theory. It's quite complicated the way people proceeded, because, like us modern feeble people, they didn't know where they were going at the time. They're doing what they could, even though they were very clever people. So it was sort of a question: could you have a theory that had these wonderful properties of gauge symmetry, which gives you constraints? It makes this coupling relate to that coupling, and so on. It gives you a theory that's well behaved up to the sky in very high energies, so very desirable, but in which this symmetry, in which you do things that you couldn't within the symmetry. And the thing that you couldn't do within the symmetry, say, is to give a mass to the electron. And as we mentioned earlier, that's because the left-handed and right-handed electrons that you have to put together to have a mass behave differently under the symmetry. So people were challenged by that problem. Peter Higgs was responding to a guess by a couple of physicists at Penn, Ben Lee and Abe Klein, who thought they had a way of doing that. And they were attacked by Walter Gilbert, later a Nobel Prize winner in biochemistry, who said, "Don't you guys know anything?" And as Ben described it to me, we were completely defenseless. And Peter Higgs's attention was attracted by that particular episode. Yeah. The other guys came to it at about the same time. A remarkable coincidence in time, through slightly different stimuli. And Higgs realized that there was something special about a gauge theory, that the common prejudices didn't operate, and wrote his very clear paper, including one in which he enunciated perhaps more clearly than other people had the necessity of a new particle, which we now call the Higgs boson, slightly unfairly to all the rest of them, and showed how you could hide a symmetry and have your cake and eat it too.
Yeah.
None of those 6 people, and I guess I've met and talked with all of them, who even in old age were quite clever, some of them are still with us, thought of applying this insight to the problem of the weak interactions. Then came some other people, including our friend Gerhard de Tooft, one of the makers of these theories, who were trying still to rescue Yang and Mills by finding a mechanism that would give mass to the force particles of the nuclear force. So that was actually his path into this problem. This goes back to your first question about the funny way we organize the material, because you get your stimulation from places that may not make any sense when you're giving the logical development of the subject. So that was his path in. And then the first person who combined things, all the pieces in a way that almost gave us the full theory of the weak electromagnetic interactions, was Steven Weinberg, right, building on some symmetries that had been emphasized by Shelley Glashow, mentioned first by Shelley's advisor, Julian Schwinger, and then required further development to turn into the theory that we know now. But that was the idea, that you could put these 2 ideas together, really came from Weinberg.
In my upcoming book, there's only, again, something I feel bad about, there's only one plot with data in it. And the plot with data in it is the number of citations per year to Weinberg's paper.
Yes.
Because no one paid any attention to it when it first came out in 1967, the paper that actually unified the electromagnetic and weak interactions.
Including, as Sidney Coleman pointed out in a famous article in Science, Steve Weinberg. Right. He was off doing other things that seemed much more promising at the time.
I mean, do you want to give the listeners a little bit of a physical insight into how what we now call the Higgs mechanism breaks these symmetries that are so important?
You probably have been searching, as I have for years, for a 25-word explanation
of this phenomenon. That's why I'm flopping it to you.
You got me.
Yeah, it is hard, but I guess the punchline is it sort of reminds us that Yang and Mills, when they treated the neutron and the proton as maybe symmetric, weren't that wrong. Like, there's a way that they could have been symmetric. It didn't quite work for them, but
that's right. And you could apply this to their theory. It wouldn't be the theory of our world, but
Yeah.
it would be a perfectly respectable theory in which there are some massive force particles.
And then,
No, it is subtle, and the second subtlety is that if you're asked exactly how the Higgs field gives mass to the electron, there are actually two aspects of that. One is, how does it happen? And that we sort of understand, although I think we do need a blackboard still to explain it.
yep.
And then the second is, how did it get the number that it is, about which we have no clue? That is one of the open questions. One of the things that the experiments at the Large Hadron Collider are showing us is that it is very, very plausible that the Higgs field, the thing that makes the Higgs boson, is responsible for the mass of the W and Z bosons, the top and bottom and charm quark, and maybe the others. But it's very frustrating because within our theory, there is no calculation you can do that will say what the number should be. It's not that we're too lazy or we haven't developed the techniques. There just is nothing. So it's coming from somewhere else, which means, luckily, there's more to learn.
Well, this is wildly out of chronological order, but when we turned on the Large Hadron Collider and discovered the Higgs, and we were all very happy, we haven't discovered anything else yet in terms of new fundamental particles. How surprising is that to you?
So you carefully qualified your negative statement, saying fundamental particles. You can define them as you have. Among the new strongly interacting particles, like the pion and the proton and the neutron, I think they're up to 86 new particles. So things are happening. Maybe not that will change our view of the fundamental laws of nature, but will guide us in understanding how those laws are implemented by nature, which is another problem I like to work on, because the problem of the Higgs boson, electroweak symmetry breaking, and so on, if you work on that, you're working on a 30 or 40 year time scale. I think for me, it was 35 years between my first fascination and the discovery, and still continuing. Whereas for these other problems, which are more like engineering problems or applied physics problems, you get to find out in 6 months or a year whether you're full of it or you got the right answer for something. So that is fun. I think the thing that has surprised me most is there is this standard model of fundamental particles interactions, the 6 quarks, the 6 leptons, the 3 interactions plus gravity still off to the side. And to be slightly lacking in respect, I know the people who made up this theory. And they're not actually gods. They're pretty good. There is this absence. It's a feature of the theory of the weak interactions as applied to the strongly interacting particles, the quarks, that the weak neutral current interaction, the thing carried by the Z boson, doesn't change the flavor of the quarks or leptons involved. And
so it doesn't change up to strange or whatever.
That's right.
Yeah.
There's a beautiful symmetry noticed by Shelley Glashow, Johnny Iliopoulos, and Luciano Maiani that guarantees that as long as the quarks and leptons come in pairs, this is the way it's going to be to first approximation. Yeah. And I would have thought, because almost any generalization of the standard model, supersymmetry, technicolor, something that doesn't have a name yet, breaks this. And so I would have thought we would have found examples of violations of this really approximate, we thought, symmetry, but we haven't.
Yeah.
So that either means that the standard model is yet more brilliant than we knew, or that there's something hidden going on that we'll discover someday. So, that's not the discovery of a new particle, but that's a crack I thought would be in our theory that hasn't cracked.
Well, yeah, this, like, when we're talking about historical incidents, we can say, oh, yes, they were very brilliant or they were very dumb. But in the present moment, we don't know the answer to a whole bunch of questions. And we know that 50 years from now, people will be saying that we're very clever or very dumb, depending on whether we guess right.
And from time to time, all of these people were very clever, but they might not have had the
Fair
whole
enough.
answer.
Yeah, that's right.
And it's our job and the job of people younger than us, both in theory and experiment, to find the soft spots and to make it better.
Well, let's rewind a little bit now, because the weak interactions which take advantage of the Higgs mechanism, and Weinberg and Salam, et cetera, helped us understand very well. The strong interactions with the quarks are, on the one hand, a more pure realization of Yang and Mills's idea. But on the other hand, what a journey that was, like, to realize that there were these particles that you can never see, and there's three of them, and they have colors.
Yes.
Where did all that start? Where's the first idea that maybe protons and neutrons have other little particles inside?
I think it came from desperation. So a different kind of symmetry, classification symmetry, or as we would call it now, a global symmetry. During the 1950s, early 1960s, people using accelerators and bubble chambers were finding dozens of particles. And there was a struggle to try to classify them in a way that would make them make sense. Some of them are strange particles, or doubly strange, or triply strange even. And people tried all sorts of symmetries. So there's a junk heap of history where people tried all sorts of symmetries that, when you had the first 7 particles, looked pretty good, but then you found an 8th particle and it didn't fit. It's not useless, because lots of those people got university tenure by writing what we now know to be wrong theories.
Very important.
So as is well known, SU3 symmetry, the flavor SU3 symmetry, was proposed by Murray Gell-Mann and Yuval Ne'eman. And then you ask yourself, well, okay, this symmetry applies, but it turns out that in contrast to isospin or other symmetries that we know about, we only see families, representations of this symmetry that correspond to the first few smallest sets that would reflect the symmetry. So where does that come from? So 2 people, George Zweig and Murray Gell-Mann, independently imagined that if you took an unseen member of the smallest family of the SU3 symmetry and you combined one of these and one of those, or 3 of these, you could make the observed particles and no more. So pretty brilliant.
Yeah.
George he's still with us, was from the beginning very mechanically minded. He thought it was compelling that these little things were real, the things that we now call quarks. Murray was more diffident about it. And the first conference I ever went to, when I was about to begin graduate school at Berkeley in 1966, as I was arriving in Berkeley, there was the International Conference on High Energy Physics, what we now call ICHEP. And in those days, any street person could pay $5 and go in and sit in the back of the room and see these heroes of the Republic talking, holding forth about things. So it's fascinating to me, partly because the heroes of the Republic, instead of talking about grand principles and contemplating their navels, were talking about little phenomena that they wanted to understand, things that were bugging them.
Yeah.
One of the talks was given by Murray Gell-Mann, and he talked about quarks, but first he explained how the quark notion of these fundamental constituents was not inconsistent to the reigning doctrine at Berkeley at the time, the bootstrap principle that all of the particles, protons, pions, kaons, things like that, were made of each other. Promoted mainly by Jeff Chu and a whole coterie of quite brilliant people who made fantastic calculational innovations to do that and to understand the strong interactions. So Murray was always diffident about this and would say, well, maybe they're just convenient mathematical fictions. But George was a true believer from the beginning. Well, both of them turned out to be right. Maybe George was more credulous and Murray was more careful, but Murray was someone who gave the name of quarks, so he wins out in the end in his own way.
I don't know if you know, but George Johnson, is a science writer who wrote a biography of Gell-Mann. at first Murray was cooperating with the biography writing process. But of course, eventually they had a falling out and they became bitter enemies, which happened with Murray a lot, apparently. But the issue over which the falling out happened was George simply pointed out that at first Murray kept saying the quarks might be fictitious. They might just be a mathematical convenience. And Gell-Mann wanted to say, no, I always thought that they were real. And,
Right.
you just read his papers.
Even though, according to George's testimony, Murray once said, "Oh, concrete quarks, those are for blockheads."
I believe it. But we have to remember, for those of us who are not expert physicists, that there was a separate move. You invent quarks. You say, okay, there's up quarks, down quarks, strange quarks. The particles that we're discovering in these wonderful experiments are all made of them. But that was a separate move to say, okay, but they come in three colors, red, green, and blue. Yes. And who in the world invented that?
So that's very complicated. Well, let me say one thing about the quarks. Consequences that were perhaps not foreseen. The trouble with the quark hypothesis was that nobody had ever seen a quark.
Yeah,
right.
That's a good one.
And so there are two aspects of that. One were people trying to prove that you should have seen them or that you didn't see them. And then there were experimental searches. The most innovative that I know about was some characters who put forward the notion that quarks were concentrated in oyster shells. And so they acquired vast numbers of oysters, disposed of the oysters in the most ecologically favorable way, and then ground up the oyster shells to look for quarks, which they didn't find. But they did get to eat a lot of oysters.
There you go.
I don't know whether the Office of Naval Research bankrolled that or who was the...
Like you said, they're all very clever people here that we're talking about.
That's right. So one of the things that led to people taking quarks seriously was that in 1968, there were experiments at the Stanford Linear Accelerator Center done by people from MIT and SLAC that seemed to indicate that inside the proton, there were little charged particles that actually behaved as if they were sort of independent. These famous experiments in which high energy electrons were scattered from the protons and really looked like they were bouncing off little hard things. They were. And so the question is, if they're acting as if they're independent inside the proton, why don't they come out? And in my generation, I guess I was either lucky or unlucky to have not had this disease. It was great sport to show that this was impossible within the context of field theory. And so people did calculations in quantum electrodynamics and theories of 3 or 4 scalar particles and so on, went on and on. The answer was always the same, that this idea that they could be independent and still held together so they were inside a coherent proton or neutron just couldn't happen in field theory. Well, naturally, people put off the hardest calculation till last. The hardest calculation was the generalization of Yang-Mills theory. It's not that hard, but it takes 2 or 3 pages to do. And miraculously, in that theory, it turned out that you could have both features, that if you hit something really hard, it looked like it was independent of the other things around it. And if you pulled on it and tried to separate them, it became harder and harder to do so you couldn't get them out. So that was a great insight of 1973 by Gross and Wilczek and Politzer. Yeah. Interestingly, there were precursors of this in the Russian literature, for example. Tuft had a whiff of it, maybe had it. Because we don't always, even in our own work, we don't always recognize when we've done something that means anything.
Yeah.
Until after somebody else becomes famous for it.
Well, you were around and involved in those days. Give us a little bit of a hint of what it felt like to be doing particle physics in that magical time when it seemed like every few months an experiment would pop up and turn the world upside down. I mean, the idea that you could shoot electrons at nucleons and see, oh, there's little hard particles inside is pretty breathtaking.
It was breathtaking. It was, I look back at, I went to Berkeley for graduate school because I didn't know exactly what I wanted to do. It was a big department that had great people in many different domains. My fantasy when I was an undergraduate was that I was going to grow up to be like Fermi and do experiments and make calculations, and that that would be fine. Well, I got to work at a laboratory named for Fermi, so
That's
that's as
something.
close as I came. It's not so bad. And then through the random things that happen when you go to graduate school, I had so I was interested in Berkeley for two reasons. One was that at the time that I was applying, I had a girlfriend from Alameda, California, who said you must go west, and then she dumped me,
There you go.
but changed my life. And the other was I had read an account in the New York Times about talk at the Washington APS meeting about people who had collided beams of electrons with each other at Stanford University. And it was very primitive. Later on, I got to meet many of the people who had done this and know them well. The idea was that with only 100 million electron volts or so, you could make these head-on collisions so it would be much more efficient than an electron colliding with a stable target, a stationary target. And in fact, to get to those energies at Fermilab took another 30 years for people to reach those energies of the electrons. Um, and when they first reported the experiment, they said, we observe one collision every 15 minutes.
Wow.
Now we're getting tens of millions per second at the Large Hadron Collider. So technology has moved on. So I was really taken with that. And then I read another article about that enterprise, which said that they were going to collide these electron beams with each other, and they didn't know what would happen. So I thought that was fantastic.
Yeah.
That you don't get to look it up in the back of the book. It's not that they said, we don't know what we're doing. It said, we don't know what happened. So I was driven to come to the West Coast for that reason. And then at Berkeley, the first people that I met that I wanted to be like were doing particle physics. It could have gone another way. But
we should mention that your book, unlike this podcast, does a wonderful job of going into the experiments, absolutely giving the experimenters a huge amount of credit. And, just to drive it home, these days we're blasé about building a particle accelerator. That's what we do, a collider in particular. But the idea of colliding two very skinny beams of ultra-high energy particles, that's not an easy thing to pull off from an engineering point of view.
To make those beams skinny is not an easy trick at all. And, both Bob and I are blessed not only to have grown up at this period when particle physics was changing so dramatically, but also because of where we've studied and worked, to be around people who have made a lot of these miracles, technological miracles.
Yeah.
So one of the people who helped teach us how to make these very strong, brilliant beams was Ernest Courant, child of Richard Courant of Göttingen, who taught me mathematical physics when I was an undergraduate at Yale, and then later was a colleague when I was helping to design the super collider that never happened. And so I got to know just how clever these people are. They may be wired a little differently from somebody who grows up to be an experimenter or a theorist in straight particle physics. But I just have enormous admiration for people who know how to make things that work.
And that particular, back in those days, what were the leading experiments that were being done? There was SLAC at Stanford. Was Fermilab up and going at that time?
No. So Fermilab had its first beams in 1972. I actually went there for a semester in the fall of 72 when there was a lot of mud. And on a good weekend, there would be beams for a few hours.
Yeah.
Some of the experiments there were using an internal target, a gas jet target inside the accelerator. Others were with extracted beams. And the big news at that time was what we started to call inclusive reactions.
Okay.
So this is something that was pushed by Richard Feynman, J.D. Bjorkane, Ken Wilson and others. Yang also was a proponent of that. And it marked a transition from the time when people studying the interactions of protons and pions in bubble chambers would look for two or three or four particles being produced in the final state to dozens. Now we have thousands, occasionally tens of thousands in the heavy ion collisions. And we were beginning to apply techniques of statistical physics rather than looking for individual resonances to try to understand what the strong interactions were really like. And I, being on the spot there, and then when I went back to Stony Brook, I continued, and then I came back to Fermilab. We were able to do things that I thought were very insightful about the strong interactions, and which stand up even today. And I remember having just moved to Fermilab, very proud of the progress we'd made. It was much more than I thought a priori would be made. And then came the discovery of the J-psi particle, which was revolutionary and recalibrated me about what was really important physics. And so I changed what I was doing at that point.
Well, this is great because that's exactly the other thing I wanted to talk about. I think that people get a little misimpression when they read a little bit of the history of particle physics. Like the J-psi particle, it was discovered. It's made of a charm quark and an anti-charm quark. And so what's the big deal? Like, okay, you've already found 3 quarks. You found a 4th quark. You know, why is that so exciting at the time?
Well, it was very exciting at the time because from that day, unless you were really recalcitrant, you had to be pretty convinced that quarks were real mechanical objects. So that may be the moment at which Murray stopped claiming they were fictional entities. And the charmed quark was necessary for this symmetry discovered by Glashow-Ilidopoulos and Majani that kept the neutral currents from changing flavor. There had to be such a thing. And then they had to come in pairs after that. So that ratified or validated that idea. People had imagined the consequences of this. Once there were neutral currents and they behaved, that was discovered in 1973 at CERN, and they behaved as specified, then the charm quark seemed like it had to be there. My colleagues at Fermilab so I was there in the fall of 72. 73, 74, my colleague Ben Lee invited me to come there once a month for a week. And during that time, he and John Rosner and Mary Kay Guy are writing a paper called Search for Charm, about why charm had to be there, what the properties would be like. And it was one of these delicious circumstances in which Tom Applequist and David Politzer, had imagined what it would be like if there were a resonance of a charm and anti-charm. Suddenly on that day, if this turned out to be true, as it did, we realized that nature had taken our collective ideas more seriously than we had. And that happens a few times in a career.
If you're lucky,
it's really wonderful.
Right. That's a wonderful moment.
I mean, you got smacked down enough, but if you find that the shortcoming in your work was to be too timid about it and that nature took it seriously, that's fantastic.
Right. And I guess I did mention, we've mentioned SLAC and Fermilab, but I do want to say that CERN had been around for quite a while, all this time.
Yes. So CERN, I was lucky to go to CERN for my first year as a postdoc at Stony Brook, 1970, 71. Everybody, including Xian Yang, was very generous to me. Yang sent me to a meeting in Dubna in the Soviet Union that he didn't want to go to, and I got to meet some of the gods of Russian physics, Podokorvo, Grivov, Fokun, and so on. I wish I'd spent more time with them. And then I stopped at CERN on the way back. And so my association with CERN goes back to that time when I was a kid that nobody knew and had never done anything. But people treated me like a grown-up and made me feel welcome from the beginning. They didn't have to because it's such a busy place. CERN was just making the transition from a place that had been created after the war, so European nations could do something together, peaceful, cooperatively, And for decades, it was the singular example of successful European cooperation. Now there are other things, but CERN has gotten even stronger in its reputation. And it had a reputation for doing sort of ponderous experiments up to a time. And then they really found their footing, and they built the first colliding beams machine of protons on protons, starting in 1970 or so. So that was operating when I first went there. And then toward the end of the 70s, they got the idea. Well, they had the large bubble chamber experiment that found the neutral currents. I was there that summer in 1973 and got to witness the deliberations within the collaboration. Well, from the outside, I wasn't privy to all of the invective, but people were really asking themselves, do we have an effect, or is it some background we haven't found? Being really meticulous, because as Jack Steinberger said, if there had been neutral currents, Fermi would have told me about them. And then the next summer, he was giving lectures on neutral currents.
There you go.
So these things are going on. CERN was really becoming a big player on the international scene, and then built the superproton, synchrotron proton antiproton collider that discovered the W and Z bosons, and has been, if not the center of the universe for us,
right,
at least one of them ever since. And it's a great place. I'll be there in a week again.
Oh, good. We haven't said so explicitly, but probably most listeners at this point know that the elementary particles come in the two kinds of fermions and bosons. And maybe they don't know that bosons are always discovered in Europe and fermions are always discovered in the United States so far.
Well, there might be an exception to that.
Okay.
And that is photon, which wasn't believed until the Compton effect was observed in the United States. And you could make an argument that the electron was discovered in Cambridge, England.
These rules are never quite completely accurate. Symmetries always have a little bit of breaking in them. But okay, so it's just a fantastic human story of the construction of the standard model of particle physics with all the fits and starts. And like you said, and this is a theme of the books that I'm writing right now, the equations are smarter than we are, and we are often taught by nature to take them more seriously than we do from Dirac onwards. But is not the word, but the standard model's been around for a while now, right? It's been a huge success story, and has put us in this weird place where our theories are better than we are. We don't have super reliable, anyway, anomalies that are pointing us to new physics. So, with that at the end of the podcast, we can speculate a little bit. What do you think about the next 50 years of particle physics and fundamental physics more generally?
Well, about the last third of our book is devoted to questions to which we don't know the answers. It is true that nothing has hit us in the face recently from the Large Hadron Collider that we fundamentally don't understand. But we do have little things like the dominance of matter over antimatter in our universe, mm-hmm. which has baffled people since at least the 1950s when they, that's another story that for people under 90 years old, I think is difficult to understand. Why, after the positron was discovered, did people think there was any doubt that there would be an antiproton? They did, and their reasons weren't actually stupid. You just have to put yourself in their frame of mind. And all sorts of what we now think of as screwball ideas have been invented to explain why we only see matter around us. But that's a real puzzle, and speaks to our existence. So how can you not be interested in that? There's the rest of the matter in the universe, the dark matter, which some people thought, I think I might have mentioned this possibility, but I didn't advocate it, thought would be discovered in the first 8 minutes of running at the Large Hadron Collider, the dark matter.
There was a chance.
It could have happened. And then there's the phenomenon of dark energy, the accelerated expansion of the universe, which is, I followed when it was happening because I was a member of a review committee at LBL, and so I was hearing the updates on this and from the beginning. And I would say that the observations of, the idea that you would measure the expansion of the universe, for which there is new news this week from the AAS meeting, was from the beginning going to be a test of the observers rather than of nature, because our cosmologist friends, and you masquerade as one of them
Sometimes.
from time to time, the inflationistas, as we call them, argued that the universe was exactly at the critical density, and so there was going to be enough dark matter to make that. And under those circumstances, since you never bet against Einstein, there's this deceleration parameter that people were going to measure, and it was going to be 2 or -2, depending on your conventions. And so that was going to be the answer. And you'd pat the guys on the head after they got the answer and said, your technique worked, very good. Except that's not the answer. So there's a place where we were hit in the face by what some people might, with reason, have thought was going to be the most boring investigation you could do, right? You're just going to check the box and say, oh yeah, Einstein guy, he's right again. Well, of course, it was Einstein plus all the other people who weren't right again, and are some of our good friends. So there are these surprises that have come up. And the beautiful thing about the development of modern physics is that what we learn about the fundamental theories of the forces and what we see out in the sky are related. There is gravity, which itself is a theory that comes from Noether's symmetry principles, although that's not how Einstein got there. So there's a great coherence among these things. And I think for all of us who are grown-ups and for our students, the notion that we try to pay attention to as wide a spectrum of these things as we can and understand how, in the same way that we've tried to indicate how a technological development might inform the way we do experiments and therefore what we think about in theory, just trying to pay attention to the whole range of what's going on makes us better at our little corner of the world.
But there are, maybe, I don't know whether it's I don't want to emphasize it too much. There are also little hints from particle physics of things that don't quite fit. And those tend to go away. But since I have you here, I mean, are you optimistic about work on these, little slightly annoying discrepancies that pop up from time to time?
I am, yes. So I would probably bet against every individual one, but hope that a few of them will persist. One that is particularly apt now at Fermilab is the measurement of the magnetic moment of the muon, which is something. So there's the electron, the muon, and similar particles have magnetic moments. The magnetic moment of the electron is something that, following Dirac, we should be able to calculate with no excuses. It's been measured to a fraction of a part per trillion. And at that level, essentially agrees with experiments. So there are all these digits in which theory and experiment agree. There is a little bit of puzzlement, confusion there, because you have to put in one number other than the electron mass to make the calculation, and that is the strength of the electromagnetic interaction, the fine structure constant. And that's been measured to stupendous precision in two places, in Berkeley and Paris, by people who are geniuses at making these measurements. And they don't quite agree in the 12th or 13th digit. And when you plug that into the calculation of the magnetic moment, of course, you get two different answers. And the measurement at the moment sits exactly between those two, which is just the way a theorist would have them. But that could be a sign of something that we don't understand. But for the muon, there is because the muon is a more massive particle, there is a much greater opportunity for physics other than quantum electrodynamics to intervene and influence the answer. And we now have a situation in which experiments first at Brookhaven, well, even before that at CERN, then at Brookhaven, and now at Fermilab, are giving very beautiful, very precise answers that don't quite line up with the best calculations we have. We know the soft spots or some soft spots of those calculations, and people are working assiduously to make them not quite so soft. There may be something great there to find out. It could be a new interaction, new kind of particles, or just that theorists are a little behind the experimenters in making our calculations as precise as they could be. So that's work being done by many really serious people, and we'll see what happens. The experiment has a bit more data than they already have that they'll report on in another year and a half or so. In the absence of a surprise there, we'll just tighten the limits on their number, and then theorists have to put up.
But as we've seen from the whole discussion we've had, we don't know ahead of time what are the places from which the surprises are going to pop up.
Right.
So I'm looking forward to whatever surprises we get next. And with that, Chris Quigg, thanks so much for being on the Mindscape podcast.
Okay, thanks a lot. Pleasure for me. Do mention the name of the book.
I will absolutely do that. Everyone should go out and read it. Thanks.
Okay, thanks a lot. Goodbye.